Okay, so taking a look at paper A23 Physics 6 from June 2009. This again is a particle accelerator question looking at a linear accelerator which had happened in the previous year. So here are the features of the linear accelerator. You can see here's your ion source, you've got an AC supply, and it's going to be accelerated across here. First question asks for us to look at that diagram, and then it says in the terminals the circles of the AC supply indicate the polarity of the instance shown in figure 3.1 with the electron in the position shown between B and C. Right, so this is an electron. The electron wants to be accelerated from B to C, which means that C must be positive and B must be negative. So that means that the bottom terminal here must be negative and the top terminal must be positive. So now that makes C positive and B negative. The electron's been repelled by B and attracted towards C. It's been accelerated across that gap. Okay? So we're asked now to explain why that is. That's the explanation that I've given. So it's repelled from the electrode B that it's leaving, and it's attracted to the next one, which is C. So the electron will be repelled by electrode B, as it leaves, and attracted to electrode C ahead of it. Okay, so it's been repelled by B, attracted by C, and it'll move across and accelerate. Why then is it necessary for the length of the tubular electrodes to increase? Well, again, if we just go back up to the diagram so that you can see, here's the diagram of the linear accelerator, and you can see we have increasing length of this. That is because as it meets its first gap, it accelerates. So it's traveling faster through B. Therefore, in order for it to come through B and be attracted to C, it must spend the same time through B, and that would be the time interval that would be in there would be half of the cycle of that alternating PD. So as it travels from B to C, it again has accelerated, so it'll be a longer time, a longer length of electrode here to be the same time inside that electrode. So the tubes increase in length, and the reason for that is so that the electron stays the same length of time in successive tubes. Okay, so the electron must spend the same length of time in successive tubes. So the tube that comes after it must be in there for the same length of time. What then is the change in kinetic energy and the time it takes for an electron leaving A to emerge from D? Right, so again we need to look at our diagram here so that we have going from A to D, and it's being accelerated. We're told that it's accelerated by a voltage of 200 kilovolts. So it's going from 200 kilovolts at each of those. Okay, so we have 1, 2, 3 accelerations. So for each acceleration then we're going to work out using the kinetic energy gained is equal to the charge, which is this time an electron, times the voltage. So that's equal to 1.6 times 10 to the minus 19 times 200,000 volts. Okay. And that gives us then a total of 9.6 times 10 to the minus 14 joules. So that's how much kinetic energy it gains for 3 of those. So that would be, we need to take that figure there and multiply that by 3 because there's 3 gaps. So it's 9.6 times 10 to the minus 14 joules. Okay. So the kinetic energy gained is equal to the charge times the voltage, and that's at one gap. If we look at the 3 gaps, then we have to multiply that by 3, and that gives us a total then of 9.6 times 10 to the minus 14 joules. Part C of this question then looks at the low energy antiproton ring accelerator at CERN and what it does. So it produces anti-hydrogen atoms, and so we've got a simple representation of normal hydrogen, and then we've got the anti-hydrogen. So we're asked to put in what this would be in the top box and what this would be. So here this is an electron, this is a proton, therefore in the nucleus we're going to have an antiproton, and circulating around that we're going to have a positron. Very simple for just the one mark there to think about that. So state one difference and one similarity between each corresponding pair of particles that make up those atoms. So each corresponding pair, so the positron and the electron that we had identified up there, they both have the same mass. Because they're identical in that way, but they will have opposite charges. Okay. So they have opposite charges, and that's really essentially the definition for antiparticles. They have the same mass but opposite charges. Okay, and that's the end of that question. Thank you.